frequency implications, just keep this equation in front of you. ZC is equal to 1 divided by j omega c. Okay. And the emphasis over here is obviously on omega. Okay. Now, if I have a voltage source for which I can change the frequency, so by definition, this is an AC source, right? Because for DC, if I want to convert this into DC, VDC, regardless of what the magnitude is, as long as it is a constant value, okay, the frequency is equal to 0. DC does not change. It's a constant value. And remember that omega is equal to 2 pi f, and f is equal to 0, and that's why omega is equal to 0. Correct? Now, substituting this into the formula, ZC is equal to 1 divided by 0 is equal to infinity. Can you see this? So for a DC setup, for a DC network, your cap is acting as an OC, open circuit. Take it to another extreme. Set the frequency to infinity, right? You used to have a cap over here, but since you cranked up the frequency so high that your ZC is now equal to 1 divided by infinity, this is equal to 0. It's as if there is no capacitor, it is acting as a short. Make sense? Okay. And then if you have a resistor over here, it really doesn't matter in this case, because what ends up happening is that your resistor has a voltage of 0 across it. There's no current flowing through it. And then if you have a resistor in this case, then the total input voltage will be applied across the entire resistor. Okay. So this is a key concept. And in transient analysis, in FE electrical as well as P power, we have to understand it inside out. Let's take a look at this set of practice problems very quickly. Conceptual problems, right? They deal with RC transient analysis. So when the switch closes, okay, when the switch closes, and remember this is DC. I want to remind you guys that this is DC. As soon as the switch closes, okay, what do you think is the voltage across the resistor? Now, the fact of the matter is, as soon as the switch closes, if the initial voltage across the capacitor is actually equal to 0, what we will start having is a flow of positive charges that are going to deposit themselves on the positive plate, and a flow of negative charges that are going to deposit themselves on the negative plate, right? Because remember, and it's easier to see it without the resistor. Assume for a second that there is no resistor. The cap is simply two neutral plates. You have access of positive charges on the positive plate and negative charges on the negative terminal of the battery, Through a simple process of diffusion, you will have, this is neutral. There is 0 charge here, 0 charge here. So the positive charges are going to start depositing themselves over here, right? And this is how the current basically establishes across a capacitor, okay, which has an electrical discontinuity. For a lot of students, understanding this concept that capacitor has an electrical discontinuity, it has an open circuit in between. How do you actually end up establishing the charges? This is the answer. For DC, this happens in transient state until the same number of positive charges exist on the top plate of this capacitor as the positive terminal of the battery, and the same number of negative charges appear over here on the bottom plate of the capacitor and the negative terminal of the battery. Okay. So this is how we establish a current flow during the transient state. All right. Think of it in terms of diffusion. So the voltage across the resistor right after the switch is closed at T is equal to 0. How will the voltage across the resistor appear? What will be the voltage across the capacitor right after the switch closes, right? So the capacitor will allow maximum current to flow through the circuit when the delta V between the capacitor's plates and the battery is highest. And if the current is the highest, right? Okay, it basically means that for a very short period of time, the capacitor acts as a short circuit. because it is allowing a lot of current to flow through. Okay, so at any given time, the source voltage is equal to the sum of the resistor voltage. Because this is a series arrangement, you only have a voltage gain over here, a voltage drop over here, and the voltage of the capacitor. So the capital V is equal to the sum of VR plus VC. So if the initial voltage across the capacitor is equal to 0, we can see that the total voltage from the source is going to drop across the resistor. So this is going to be capital V is equal to VR. Initially, the VC is equal to 0, capacitor acts as a short. The current through the circuit after the switch is closed. So the current through the circuit will simply be equal to the VR divided by R, okay? Which is simply equal to the capital V divided by R. So the largest amount of current actually flows when the switch is closed, okay? So this is equal to VR divided by R, which is equal to V divided by R. Steady state. Now, steady state is established when, let us assume that the capacitor is charged more or less the same value as the battery. Now, when I have V at this terminal across the capacitor, across the resistor, VC, which is equal to V, and then this terminal is already V, is there any delta V across the resistor? There is no delta V across the resistor. If the delta V across the resistor is 0, so this, going back to this equation, V is equal to VR plus VC, okay, the delta V across the resistor is equal to 0, and V is equal to VC because the capacitor has been charged. So now the VR is equal to 0. VC, the voltage across the capacitor, is equal to the charged voltage, which is the source voltage. There is no reason for current to flow because current was previously flowing as VR divided by R. Okay, and VR is equal to 0. So there is no delta V across the resistor. There's no current that is flowing, and the capacitor is now fully charged. And how will the capacitor behave if we had an AC source? This cycle will keep on repeating in the positive and negative charges, and the capacitor charge will keep on flipping from positive to negative, from negative to positive. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, StudyforFE.com.